Hello everyone, and welcome to Earth Archives. Today, we're taking you on an in-depth journey into one of the universe's most mysterious and awe-inspiring phenomena, the birth of singularities and the secrets of black holes. From the mass mysteries of Earth and the Sun, to the extreme challenges of white dwarfs and neutron stars, all the way to the infinitely dense singularity at the center of black holes, we will gradually uncover the secrets behind the cosmic balance and collapse of celestial bodies. Want to know why the Earth doesn't get compressed into a tiny ping-pong ball? How the Sun manages to burn as a gigantic furnace for billions of years? And just how mysterious is that black hole singularity that not even light can escape? Let's begin this breathtaking cosmic adventure now. If you're interested in topics like cosmic singularities, black holes, astronomy, and nuclear fusion, be sure to subscribe to our channel and turn on the notification bell to stay updated with the latest discoveries in cosmic science. Today, we're going to talk about a mysterious and awe-inspiring cosmic topic, the birth of singularities. This is considered one of the ultimate mysteries in astronomy, involving everything from our familiar sun to black holes born under extreme gravity and the densest, most incredible objects in the universe. Now, going back, Newton's law of universal gravitation was the key that opened the door to all this thinking. Since Newton proposed gravity in the 17th century, people have wondered, if gravity were really that strong, would the Earth be compressed by its own weight into something as small as a ping-pong ball? At first, this sounded a bit funny. After all, we walk freely on Earth every day. So how could it possibly collapse to such a tiny size? In fact, the Earth doesn't collapse because its mass isn't large enough to generate enough gravity to compress atoms beyond imagination. It's like a group of electrons inside, desperately keeping their distance to prevent atoms from being squeezed together, creating a remarkable resistance to compression that keeps the Earth stable. This interesting question sparked scientists to dig deeper and gradually uncover the secrets of the internal balance within celestial bodies. Why doesn't the Earth collapse? The key lies in the fact that although Earth's mass is huge, it's still not enough. Its own gravity isn't strong enough to compress atoms any tighter. The repulsive force between electrons inside atoms acts like an invisible shield, layer by layer keeping atoms spread apart so they don't get squished flat. Meanwhile, the atomic nuclei are like sturdy building blocks, solidly supporting our home, the Earth. This microscopic force and the macroscopic pull of gravity reach a clever balance, allowing us to live safely on Earth without worrying it might suddenly shrink into a tiny ping-pong ball overnight. Next, let's turn our eyes to the brightest star in the universe, the Sun. Its mass is an astonishing 330,000 times that of Earth. Imagine if Earth were a basketball, then the Sun would be the entire basketball court. Such an enormous mass brings incredible gravity, squeezing hydrogen atoms in the Sun's core so tightly they're packed like people in a super-crowded elevator. This extreme pressure and heat cause hydrogen nuclei to fuse together, igniting a nuclear fusion fire that has burned continuously for billions of years. It's this blazing hot pot that allows the Sun to constantly release light and heat, illuminating and warming our entire solar system, becoming the essential energy source for all life. The temperature at the Sun's core soars to an incredible 20 million degrees Celsius, like a gigantic furnace that never goes out. Every second, the Sun consumes about 4.3 million tons of mass through nuclear fusion reactions, converting that mass into light and heat that radiate out into the depths of the universe. It's this continuous flow of energy that powers life on Earth, lighting up every morning and warming every corner. However, the Sun's fuel supply is not infinite. Scientists predict that in about 5.1 billion years, the hydrogen inside the Sun will be depleted, meaning nuclear fusion will no longer be sustainable. When that day comes, the Sun's gravity will take over, causing it to collapse inward, much like a balloon slowly deflating. But this collapse is not a total catastrophe. During the process, helium will gradually become the new fuel, and the Sun will enter a phase of alternating expansion and contraction, like a cosmic dance. This process will cause the sun to swell into a red giant, expanding to about 100 times its current size, becoming enormous and magnificent in appearance. Because its surface temperature drops, the once dazzling white light will gradually shift to a gentle red glow. During this red giant stage, the sun's brightness will fluctuate, and its diameter will expand and contract unpredictably, much like an old friend with a moody temperament, filling the universe with dramatic and ever-changing tension. As the helium fuel inside the red giant gradually runs out, nuclear burning in the core slowly ceases, and the core begins to contract into a white dwarf. This white dwarf is the remnant of the star's life cycle, primarily composed of carbon and oxygen, and it emits a faint white glow on its surface. Although the white dwarf appears calm, changes are still quietly occurring inside. It is gradually synthesizing iron. Iron is a very stable element, but precisely because of this stability, it can no longer provide the energy needed to sustain the star's nuclear burning. This means the white dwarf will gradually lose its brightness and eventually enter a dim and cold state. The nuclear fusion of iron is not like that of hydrogen and helium, which can release energy. Instead, it acts as an energy black hole. It requires more energy to occur than it produces, making it impossible for the star to sustain its flame through fusion. When effective nuclear fusion can no longer take place inside a white dwarf, gravity begins to compress it inward once again. However, this time, the white dwarf will not be compressed indefinitely like ordinary matter. The reason lies in a mysterious force known as electron degeneracy pressure. This is a fascinating phenomenon in quantum mechanics. Due to the Pauli exclusion principle, electrons cannot be forced too close to each other. Like invisible quantum pillars, they silently resist the onslaught of gravity. This force becomes the white dwarf's final line of defense, allowing it to remain stable and not be completely crushed by gravity, making it a unique and resilient celestial body in the universe. That's right, electron degeneracy pressure does have its limit, about 1.4 times the mass of the Sun. This boundary is known as the Chandrasekhar limit. If the mass of a star's remnant does not exceed this limit, the white dwarf can hold steady and won't be crushed by gravity. And this is exactly the fate awaiting our Sun. When the Sun finishes its nuclear fusion, it will slowly cool down into a white dwarf, lasting for billions of years, eventually becoming a black dwarf, a completely dark, cold, and silent dead star, drifting quietly through the universe. This is the gentlest scene in the life cycle of stars in the cosmos. No violent explosions, no all-consuming black holes, just a quietly resting cosmic elder. You can totally imagine it. The core of a black dwarf would be made of carbon and oxygen. Under extreme pressure, these carbon atoms would pack tightly together, forming a crystal structure like diamond. In other words, the surface of a black dwarf might resemble a gigantic, sparkling diamond planet, a dazzling treasure the universe has gifted us. Indeed, neutron stars are truly the supernuclei of the universe, with densities so staggering they defy imagination. When so much mass is compressed into a space the size of a golf ball, the gravitational field becomes extremely intense, so strong that even light cannot travel in a straight line but is bent along strange paths. Scientists call this bending of light the gravitational lensing effect, which allows us to indirectly observe the existence of these mysterious objects. Moreover, neutron stars spin at incredible speeds, sometimes hundreds of rotations per second, forming what are known as pulsars. Like cosmic lighthouses, they emit powerful electromagnetic waves at regular intervals, providing astronomers with abundant clues for research. These ultra-dense neutron stars serve as the best laboratories for understanding extreme physical environments and bring us closer to uncovering the universe's deeper secrets. When a neutron star's mass exceeds the Oppenheimer-Fokoff limit, the neutron degeneracy pressure that once supported its existence completely fails. Gravity's force is no longer resisted by anything and begins to compress matter infinitely. This infinite collapse leads to the birth of a breathtaking celestial object, a black hole. At the center of a black hole lies what we call a singularity, a mysterious point of infinite density and zero volume, where space-time is warped to the extreme and even light cannot escape its gravitational grip. The existence of singularities challenges our understanding of physical laws and even evokes thoughts of parallel universes and higher dimensional spaces. At the center of a black hole lies the universe's most mysterious and captivating character, the singularity. Imagine a point with an unimaginably high density, yet a volume so tiny it almost disappears. That's the astonishing nature of a singularity. Here, space-time is warped beyond recognition, and the physical laws we know completely break down, as if entering a completely different realm. Scientists are still exploring the nature of singularities, but they generally believe that at this tiny point, the usual concepts of space and time no longer apply. Even the solid matter we see around us may be transformed into another form of energy stored there. Imagine all the stardust, light, and even entire planets swallowed by the black hole are reorganized within the singularity, becoming a kind of invisible yet powerful energy, like the universe's ultimate treasure trove. What's even more exciting is that speculation about singularities is wildly diverse and full of sci-fi intrigue. Some researchers suggest that a singularity might be a crossroads to parallel universes. In other words, through this mysterious gateway, we might glimpse or even travel to another universe. This idea feels like something straight out of a sci-fi movie, sparking endless imagination about the infinite possibilities of the cosmos. According to M-theory, the mysteries of the universe are far deeper than we imagine. Our universe actually has 11 dimensions. However, we can usually only perceive 4 of them: 3 spatial dimensions and 1 time dimension. The remaining 7 dimensions are tightly hidden at the incredibly tiny Planck scale, like invisible folds of paper in the fabric of the cosmos, impossible to see or directly sense with the naked eye. Remarkably, scientists speculate that inside the singularity of a black hole, these compressed extra dimensions might burst forth, creating an 11-dimensional world beyond our comprehension, turning the singularity into a mysterious space that transcends dimensions. Imagine the universe as a snake biting its own tail. Its surface seems to extend infinitely, yet somewhere it loops back on itself. As we approach the infinite boundary of the universe, we might ultimately encounter its infinitely small limit, and that infinitely small extreme is the singularity. It is not just the center of a black hole, but also the ultimate end and beginning of our understanding, a final frontier for scientific exploration. The mystery of the singularity not only challenges our understanding of space and time, but also reminds us that the true nature of the universe may far exceed our imagination. For now, we can only rely on theoretical models and astronomical observations to speculate about the real appearance of singularities. It is a quest without definitive answers, and one of the greatest challenges in modern physics. Speaking of why the Earth doesn't get crushed like a ping-pong ball, there's actually a superhero quietly guarding it: electron degeneracy pressure from quantum mechanics. The term sounds complicated, but you can think of it like electrons crowded in an elevator, each wanting their own personal space and refusing to be squeezed too close. According to quantum rules, electrons follow a strict law that they cannot occupy the same state simultaneously, making them like roommates who stand their ground, pushing each other but never giving in. This force is the secret weapon that allows the Earth to resist its own immense weight and avoid being crushed into a dense lump. Although the Earth looks very large, it is actually tiny on the vast scale of the universe. Earth's mass is about 6 times 10 superscript 2 kilograms, an incredible number, but compared to our Sun, it's smaller by a factor of 330,000. This huge difference in mass is not just a numerical comparison. It is a key factor in the birth and evolution of life in the universe. Without such a scale difference, Earth wouldn't be able to maintain a stable state, nor could it nurture the rich diversity of life. The Sun's core isn't an ordinary flame. It's more like a boiling cosmic hot pot, filled with intense energy explosions. The temperature here reaches millions of degrees, and the pressure is extreme, causing hydrogen nuclei to continuously fuse into helium, a process called nuclear fusion. This is not simply burning, but a raging energy frenzy that releases enormous amounts of light and heat every second, sustaining the entire sun and keeping it stable. During nuclear fusion, mass is gradually converted into energy, causing the sun to slowly lose weight. But this process is so gradual that the sun can steadily burn for billions of years. Now imagine a situation about 5 billion years from now, when the sun's hydrogen fuel gradually runs out, and the fire in this cosmic hot pot begins to fade. The energy from nuclear fusion can no longer fully resist the pressure of gravity, so the sun starts to contract inward. As it compresses, its internal temperature rises, igniting another type of fuel, helium. It's like when cookies start to burn and smoke around the edges while baking. The sun then enters the wild phase of a red giant, swelling and growing brighter, but undergoing intense internal changes. This is the cosmic chef's fascinating process of preparing the hot pot, allowing us to witness the cycle and transformation of a star's life. During its red giant phase, the sun truly becomes the universe's greatest theatrical performer. When it expands to an astonishing size, it might even engulf nearby planets, including Earth, a scene like a vast cosmic storm. The sun's outer shell balloons enormously, while its core contracts tightly. Inside, the whole star behaves like a Tai Chi master, gracefully pulling between explosion and collapse, with forces clashing yet delicately balanced, creating a unique and dangerous dynamic equilibrium. As the nuclear fuel is gradually exhausted, the sun's core will finally shrink into a white dwarf, the last static remnant of the sun's life. Though the white dwarf has a considerable mass, its volume is extremely compact, roughly the size of a city, with an unimaginably high density, composed mostly of carbon and oxygen. These leftover stellar remnants emit a pure white light and represent one of the most common end states for stars in the universe. Although white dwarfs once shone brightly, their light is not eternal. Without the support of nuclear fusion fuel, a white dwarf can only slowly radiate away its residual heat. After billions of years of gradual cooling, it will eventually become a dead star in the universe, a black dwarf. Black dwarfs no longer emit light or heat. They simply drift quietly in the depths of space, like witnesses to frozen time, silently guarding the stories of the past. When it comes to black dwarfs, scientists are especially curious about what their surfaces might look like. Interestingly, because white dwarfs are primarily composed of carbon, and under extreme pressure carbon crystallizes into diamond, some speculate that the outer layer of a black dwarf could be covered in sparkling diamonds, making it one of the most magnificent treasures in the universe. Truly breathtaking. However, if a white dwarf's mass exceeds 1.4 times that of the Sun, the so-called Chandrasekhar limit, the electron degeneracy pressure that supports it will no longer withstand the immense weight. As a result, electrons get squeezed into atomic nuclei, combining with protons to form neutrons. This process gives birth to a mysterious and even denser object, a neutron star. Neutron stars are truly the superdense monsters of the universe. Their density is so mind-boggling that a single cubic centimeter of neutron star material can weigh hundreds of millions of tons. This density is like compressing an entire city into the size of a ping-pong ball. Just imagining it sends shivers down your spine. Even more astonishing is the neutron star's incredible spin rate, often rotating dozens of times per second, like a cosmic lighthouse spinning at high speed, emitting intense radiation waves and becoming one of the brightest and most mysterious signals in the universe. However, this superdense neutron star also has its limits. If its mass continues to increase beyond the so-called Oppenheimer limit, somewhere between 1.5 and 3 times the mass of the Sun, even the powerful neutron degeneracy pressure can no longer resist the relentless crush of gravity. When pressure fails against gravity, the entire neutron star collapses, ultimately forming one of the universe's most mysterious and extreme objects, a black hole. A black hole is like the ultimate trap in the cosmos, where not even light can escape. It becomes the endpoint for all matter and information, symbolizing the final frontier of astrophysics. Black holes are undoubtedly the most awe-inspiring and enigmatic objects in the universe. Their gravity is so strong that even light cannot break free, as if an invisible dark trap has been set, holding tightly onto any matter and light that come too close, preventing their escape. At the core of a black hole lies the ultimate existence, known as the singularity. A singularity is no ordinary celestial object. It is the ultimate limit where the laws of physics completely break down. There, the density becomes infinite while the volume approaches zero, and time and space lose all their familiar meanings. This point is one of the deepest mysteries of the universe, filled with incredible and enigmatic qualities. Some even believe that the singularity might be a gateway to parallel universes, a stage where the extra 11 dimensions predicted by M-theory truly manifest. Together, singularities and black holes represent the ultimate boundaries of our cosmic understanding. Although we have various theoretical models and mathematical tools to infer their existence, so far there is no way to directly observe these extreme regions of space with current physical instruments. This profound mystery fuels the relentless passion of countless scientists, driving them to explore day and night, hoping that one day they will uncover the secrets deep within the universe and reveal its true nature. Has today opened your eyes to new wonders? From the electron degeneracy pressure holding up our Earth, to the fusion flames powering the sun, and from white dwarfs and neutron stars to the ultimate challenge of black hole singularities, each stage reveals the universe's magic and grandeur. The singularity isn't just the end of physical laws. It might also be a mysterious gateway to parallel universes, keeping our understanding of the cosmos forever filled with mystery and anticipation. If you enjoy this kind of deep science content, be sure to subscribe, like, and let us know in the comments which cosmic mystery fascinates you the most. Also, share this video with your science-loving friends so you can explore the infinite wonders of the universe together. Thanks for watching, and see you next time. Ignite your curiosity. Explore the singularities of the cosmos.